So we're in section 6.1. 6.1 is about discrete random variables. And, well, I guess we have to define some terms. So things we have to worry about. Discrete random variable. Here we go. A random variable is nothing other than a number associated with each outcome of a random experiment. So really it should be some kind of measurement you make at the conclusion of the experiment. We use letters like capital X, capital Y, capital Z to represent random variables. So we use small letters like X, Y, and Z, lowercase, to represent values. We use those capital letters to represent random values. So you could say X could represent, pick anything that you think is random, it has to be a number. The roll of a die, the sum of the faces of two dice, the height of a plant after 2 weeks, the score on an exam, things like that. Letters like X, Y, and Z represent things that are random. Once they're observed, they're not random anymore, but before you run the experiment, they're random. So before we see it, we call it capital X. After we see it, we might call it small x, because it's a number now that we've seen. A random variable is called discrete if it has either a finite or countable number of values. Often the values are positive integers, or just integers. So things like integers, they could go on forever, but they're considered countable. Basically because you can count them and you imagine to count everything. Things that aren't countable are things that appear to be associated with intervals in the real line, like the height of your child when they turn 2 years old. It's a range of values, and if you measure it accurately, it could be any number in that range. Maybe from 2 feet to 4 feet tall might be the range of values you might see for a child. In that situation, the random variable is called continuous. A random variable is called continuous if the possible values fill an interval of the real line. Okay, so we're talking about discrete random variables. The reason we're talking about discrete by itself and not continuous at the same time is the way we find probabilities for discrete random variables and for continuous random variables involves different quantities. So for discrete random variables, we can write probabilities down. For continuous random variables, we have probabilities just for intervals, not for particular values. So it's a slightly different kind of operation. So we're just going to talk about discrete for now. Here are some examples of discrete and continuous, though, before we move on. Discrete, pip showing on a die, face showing on a coin if we label it 1 for heads, 0 for tails, winnings of a slot machine pull. Mostly 0. Sometimes you get your money back. Depending on the machine, you might be able to get 5 or 10 times your money back. But there's only a certain number of outcomes that can happen. Now maybe there's some type of giant jackpot, but that jackpot is some number. It might depend on how much money's been put in the machine, so there might be a lot of possible numbers for the jackpot. I don't know. I don't play slot machines that much, but I figured you put a quarter in, you can't get any possible number out. So it's probably a certain number of quarters, which then would be countable because it's the number of quarters that you get back. Here's some continuous random variables. Speed of a car on Highway 50, measured accurately. Weight of a newborn, measured accurately. High temperature on a random day. All these kinds of measurements where they're not forced to be in certain specific values, where they're allowed to be in an interval of the real line, would be called continuous. The probability distribution. So that's how do you compute probabilities for outcomes or events? We need a way. It can be described by a table, a graph, or a formula. So you could have a table of values and their probabilities. You could have a graph of that table, or you could have a formula that says for whatever value you're interested in, you compute the probability by putting it in this formula. Take the number and stick it in a formula. That'd be nice. So to head in that direction, we say for discrete random variables, we write this thing called P of x. So x is a possible value. P of x is the probability of that value. Oh, it says it here. That's the probability the random variable takes on the number x. So this is a small p, and that's a big P. That's P, that's an event. X is some number. This is a function. You put a number in, you get a probability out. That one is kind of too. Maybe it's shorthand for that. And then there's two things. Sometimes they call that a probability mass function, but I'm not saying it. I'll have to erase my words. For this function here, if I sum the probabilities for all possible values, I get 1. So that's because that's how probability works. If you've got all the possible values and you have the probabilities associated with the values and you sum them, you're supposed to get 1. And then those P of x's are supposed to be probabilities. Probabilities have to be between 0 and 1. Otherwise, they're not probabilities. So that probability function, the values have to sum to 1, and the values have to be between 0 and 1. I think we've seen that happen to us before, but now we're being a little more formal about it. Any P of x satisfying these two conditions, 1 and 2, is called a legitimate assignment of probabilities to the random variable. So that just means it hasn't broken any rules of probability. You could maybe have a random variable that has those particular values. You might be able to design an experiment where those numbers for probabilities actually happen. It's not an impossibility. These have to happen for things to work out. Anytime you assign probabilities to something, the probabilities have to sum to 1, and they have to be between 0 and 1. And if you don't do that, then we can't proceed and do anything, because it's not a reasonable way to assign probabilities, because you could never make that happen in practice, because they have to sum to 1 and they have to be probabilities. So we check that before we do anything further when we're looking at probabilities assigned to that we think is, we have a definition where we think we've assigned probabilities to a random variable. We want to make sure we've done it correctly, and we want to make sure they sum to 1 and they're between 0 and 1. And we'll move on from here. Here we go.